Hello everyone, Dr. Ziata here. This video tutorial is about 2D transient heat transfer analysis in ANSYS Workbench, and topic is transient heat transfer through double pane window. So that is a double pane window. Conditions are given and statement is a double pane glass window shown in the figure consists of two 4 millimeter thick layers of glass. So here is one on the inner side and one on the outer side, two layers. Thermal conductivity of glass is 0.8 watt per meter per degree Celsius. Density is 2500. Specific heat capacity is 800. And that two glass layers, they are separated by 10 millimeter thick stagnant airspace. So that is airspace in between them. Thermal conductivity of air is 0.025. Density is 1.2. Specific heat capacity is 1005. The inside room temperature is Ti infinity 20 degrees Celsius with Hi 10 watt per meter square per degree Celsius. So convective heat transfer coefficient for inside air is 10 and the outside temperature T O infinity is -10, outside temperature is -10, and convective heat transfer coefficient for outside is 30 watt per meter per degree Celsius. And assume height of the window as 30 millimeter, although that is unrealistic, but for 2D analysis, so that is assumed as 30. So determine temperature T1, T2, T3, T4. So T1 that is on the inner glass and that is on inside, then at interface. T3 is at interface between outer glass and air, and T4 on outer surface of glass. So this is problem 13.9 from chapter 13, heat transfer and mass transport, from the book A First Course in the Finite Element Method, Daryl L. Logan 6th edition. So I am going to solve that heat transfer analysis or this problem in ANSYS Workbench. So this is fifth video of the series. So I have already few videos on steady state heat transfer analysis, and they are available in this ANSYS Workbench thermal analysis playlist. So steps to perform transient heat transfer analysis in ANSYS Workbench. The first is the project, then engineering data, geometry, and then different steps in geometry, then model, different steps in model, then setup, that is analysis, and then solution, and then the results. So for transient analysis, so that is the one step which is not necessary, but I am going to use it here. So these are the steps which need to follow. So I am going by step in ANSYS Workbench. First step is to start project, and that is a thermal transient. So that is Workbench, and here analysis systems. In analysis system, that is transient thermal. So if I double click on that, so you'll see that is a transient thermal, and then there are 7 steps here as I described before. 1, 2, engineering data, geometry, model, setup, solution, and then result. So I'm going to save it somewhere in my computer. I have saved that as double pane window in my computer. Next step is in engineering data, add materials. And for transient heat transfer analysis, density, thermal conductivity, and specific heat capacity are required. So double click on engineering data. When you're going to double click on engineering data, so then density, thermal conductivity, and specific heat capacity are required. So click here to add material. So let's say material is air, and for air, drag density, isothermal, isotropic thermal conductivity, and then specific heat capacity. So then need to add values. So for air, density is 1.2, and the units you need to check that. And then thermal conductivity of air is 0.025, and then specific heat capacity is 1005. So these are the parameters which are required. Similarly, I'm going to add glass here as well. So two materials, air and glass, they have been added. And then once they are being added, so I'm going to save it. So once save, and then you can close that. Now you can see there is a tick on engineering data. Next step in the geometry, need to create geometry, and that is analysis type is 2D. Click on geometry, and here the property is 2D, and then design, start new design modeler, and right click on geometry. So right click on that, and then new design modeler. It will take some time to open. That is design modeler, and in design modeler, next is to start sketch, preferably from using hotter surface. So I'm going to start from the hotter surface, which is glass, left glass, or I'm saying it as inner glass. So I want to draw it in XY plane, and that is the Z is facing, and then because most of dimensions are in millimeters, so I'll select units here as millimeters, and then here I'll start with XY plane, and then here you have sketch. Before start, go to setting, turn on grid and snap, and then major grid spacing, leave that as, let's say 10. No, 10 is too much, let's say 2, and then 2 minor steps per major. So then draw a rectangle. So I am going to start drawing a rectangle. So the thickness is 30 millimeter. So that is 4. Now that I have drawn it, and then I'll go dimension, display dimension, and then in journal, I need to add dimensions. So that horizontal dimension is 4 and the vertical is 37. So I need to change that. Okay, so now that one, 4 millimeters, 4 millimeters by 30 millimeter, that is being, because here you can see that it is 4 and the other dimension is 30. So that is drawn. Then model, here the sketch one, click on the sketch one, and then once you have clicked on that, so then go to concept, surface, this is from sketches. Here you need to apply and then generate. So that first surface has been generated. Now that in the geometry, the first step is done. The next one, sketch, colder surface, dimension, concept, and then before generating, you need to go operation, add frozen. So next object to sketch is air, and its width is 10 millimeter. And for that one, need to start a new sketch here, that is sketch 2, And for that one, go to sketching and once again rectangle. So, and then that rectangle need to be 10. So I can add dimensions to that. So that one is 10 and the other one is obviously 30. Okay, so go to modeling, that is sketch 2, and then concept, surfaces from sketches, apply, and here operation, that must be add frozen, and then generate. So now that one surface is generated and next other surface is being generated. So that is the surface body, then the other surface body, and next one is outer glass. So the thickness of the outer glass, width of the outer glass is 4. So for that one, again, start a new sketch, sketch 3. In sketching, drawing a rectangle, and that is a rectangle. And to verify its dimensions, so need to add here its dimension, and that is 4. So its dimension is 4. Now go to the modeling, sketch 3, concept, surface from sketches, and then is a base object apply, and here add frozen. Okay, and then generate. So now 3 surfaces are generated. So the surface body 1, I am going to say it as inside glass. The next one is air. And the third one is outside glass. So it can be clearly seen by go to the setting and then so here you can see. So these are the surfaces. So this geometry part is now done. Next step, need to go to model, and for that one here double click on model, and it will take some time to open a new window. So that is model, and it contains all that model setup solution and results. So they are all here. Okay, so the first step in the model need to go geometry and then assign materials. So for that one, there's a question mark on geometry. So for inside glass, so there's a question mark on geometry, and then for inside glass, so material need to assign, that is glass. Then for air, need to assign air, and that is a surface body which is outside glass. So for inside glass, that is inside glass. Then is air, then that is outside glass. To find these temperature T1, T2, T3 and T4, and for that one I'm going to create a path right in the middle somewhere. So now in the model there is a construction geometry path, and I'm going to give the name as path A, and now it's x coordinate. So for that one, I need to check that what is the coordinate system for that body. So then origin is somewhere here, and it is y coordinate is 15 millimeter, and then here that the total length is 18 millimeter, and then that is 15. One thing I forgot, when you go to, come in the model, so then in the home, so you can set units. For sketch, I selected the units as millimeters, but for this model, I'm going to select because here I need to apply properties like for this glass, its properties, so they are in like the standard units. So that's why here in the home units, that should be the standard metric, meter, kilogram, second, or otherwise you can, from here, you can set the units. So now the path right in the middle, mid height is created. Next step is to set connection between those surfaces. And for that, contacts, go to contacts, contract region, and then type, I'm going to use here bonded. So then here you have connections. So in the connection, contact, so contact region 1. So that is the contact region 1 between inside glass and air. And contact here is bonded. So then you can change it to if any other required. And that is the contact region 2 between glass and outside surface. So that is contact region 2. Next step is mesh and the element size and to generate. And for that one, here you have mesh. Okay. And then there is an automatic mesh with the default like some size. So I want that 1 millimeter element size. So 1 e power minus 3. So that is element size with that one. And then in the mesh module, mesh, so generated. So that is mesh generated with element size of 1 millimeter. So next step is in the setup and in the transient thermal transient need to apply boundary conditions. And there are two boundary conditions, one for inside. So in the environment tab, go to convection, and then you can name that edge name and scope geometry edges and the definition, film coefficient and temperature are required. So now need to apply boundary condition here. And for that purpose, in the environment, convection. So that is convection. I'm going to rename that convection as inside. Inside temperature is 20 and HI is 10. Outside temperature is minus 10 and HO is 30. So here convection inside, it's a scoping method geometry selection. So I am going to select that edge applied, so that edge, and then it's a type convection. So the film coefficient for inside is 10 and the temperature inside is 20 and its units are watt per meter square per degree Celsius. So that is for inside. And then for outside boundary condition, right click here, insert, and then convection. And I'm going to name that as outside. Okay, so geometry selection, I'd select that edge, apply, and that's applied on the one edge. And the outside film coefficient is 30 and outside temperature is minus 10. So now uh, boundary conditions are applied both on inside and outside, both on inside and outside. So now the next step here in analysis setting, you need to add number of steps. So number of steps are basically that is based at how much is the time for transient heat transfer analysis. So for transient heat analysis, heat transfer, so initially, uh, like the heat transfer is actually transient, but uh, it is solved as steady state because that solution is easy. But all that transient heat transfer after some time that reach steady state condition. So then how much time is required to get that steady state condition? That is a question. So here in the analysis setting, so number of steps. So let's say here I can go with one, but that is a problem here. The big problem is that how much is the time? when the solution is going to converge. So to calculate that time or to estimate that time when the solution is going to converge, then we need to perform an analysis, steady state thermal analysis to get the results. And then again, we need to set a time for transient to check when the solution is going to converge. Although that is not sometimes required, you can set some infinite time like let's say 1 hour, 2 hour, or any infinite time, and then the solution will stop automatically. Like not automatically, but you can set that when the solution is going to stop. But I'm going to now start another analysis here, and that is steady state thermal. So now you can see that there is a steady state thermal, and for that steady state thermal, I need to apply those boundary conditions again here. So now for steady state thermal, I am going to solution and in thermal temperature of the whole body, and then I am going to solve that one. So it will take relatively smaller time. So that is solved. So the maximum temperature on that side is 14.479 and the minimum temperature is that one. So then this is used as a reference to check if the solution is going to converge at some specific time. So let's say here in the analysis setting, I'm going again and I am going to set that as 1 hour, which is 3600 seconds. And then for this solution and for the solution, temperature for whole of the body, and then in the solution, I right click here, insert thermal temperature, and then temperature along that path A. Because here in the construction geometry, that is path A, so that temperature. So now I'll keep that temperature from the steady state as a reference. Okay. So now that solution and solve. So it will take time depending upon that how much is the number of steps requested, and then based on that how much is mesh, and then computing capability of the machine. So you can see that the progress is 1%. So it will take some time to solve that one. The last step is to see results and results about that path. So one thing I forgot to mention, when you have multiple systems, so now transient system, for that transient system, the first three steps, so they are now gone into steady state thermal. So for that one here, that is, I'm going to close that transient for some time. That is a steady state thermal. And for that one, that is a temperature distribution. And that is a temperature along that path A. So the temperature at the outside of uh, inside is 14.49. So analytically, at the end of that book, the answer for that T1 is 14.5. And then at 4, that is 14.272. And in the book, it is 14.2. And then at 14, it is minus 7.88. In the book, it is 7.88. And then finally, on the outside, it is 8.15. So that is along the path. So otherwise, you can also check that one by using probe. So that is the outside there. Then that is the interface. Then that is the second interface. And then that is outside. So that is 14.47 at T1, that is 14.5. Then the other one 14.204, that T2 is 14.2. Then T3 7.889. So that you have 7.88 and then 8.15. so which is approximately, yeah, 8.15. So that way you can verify the results. But this steady state thermal is just used as a reference here. But our main objective was to uh, check the steady state thermal so that results from the steady state thermal, so that in the analysis setting you can substitute the temperature. So I run it for 1 hour, and after 1 hour, like here, the time number of steps 3600 correspond to 1 hour, so it is going to converge for 3600 steps. So that is temperature about that profile, about the path, and the values here, like at 0 it is 14.53, and then at 10 it is 14.2, similarly at 14 7.87, and then on the outside it is 8.153. So the results, they are well converged. So now I'm going to put that probe on overall wall. uh, if I click on temperature, and then here you'll have that values of temperature 14.52, that is for transient, and then temperature on the overall wall 14.5, 14.2, 7.794, 8.153. So these results are slightly different compared to the results of, and I'm not saying that, but they are a little bit different from uh, the results of steady state. And you can see here, so here you can see that that is the time, and that's the times. These are the steps. So, like for 3600, the solution, the maximum and minimum value, and they are like they start converging. Okay, but there is not much difference. Like for 3500, so let's say for, so they start converging, but it will take a lot of time. And here you can see that from here you can see that these uh, the average temperature is the blue one, then maximum is the green one, and the minimum is blue one. So they are somewhere like uh, after 2500, there is not significant change in those. So it means that they have converged some. So here is the temperature solution versus time. So you can see that somewhere around that like 3500, the solution is converged, although there is not significant change in the red line, which is the minimum one after somewhere 2800. But that maximum temperature is keep on decreasing. So these results are well compared with analytical results. So it means that both steady state analysis results and transient analysis results, they match with analytical results. So it is a summary of all that. So first, need to start transient thermal transient project, and then add materials. So there are two type of material, one glass and one air. So density, thermal conductivity, and specific capacity are required for that. And geometric analysis 2D, and then you need to preferably start from the hotter surface first, and then the colder surface. And while uh, this concept, you need to, in operation, you need to add frozen instead of add material. Then geometry, in the geometry you need to go and assign material to different geometry, and then paths need to be created in construction geometry so that you can view the results. And then you need to check connection, and connection type should be bonded for that. And then element size depends upon that, uh, depending upon computation, so you can set that element size. But like as like for I set that element size as 1 millimeter, and then the solution is going to converge, because in both steady state analysis and then transient analysis, the results, they are very much similar to the analytical results. And then in the setup, you need to apply boundary condition, and that is the environment. In the environment tab, connect convection, and then need to apply film coefficient and temperature, and then the same one need to apply for inner and outer. But analysis setting, number of steps you need to define, and number of step uh, is your choice, or you can perform a steady state thermal analysis to see that what the solution you are getting, and then need to increase the time in analysis setting of thermal transient. So when the solution start converge, and then the solution temperature uh, contour plot of the whole body, and then along that path, and then finally to solve it and then get results about that path. So I hope you like this video. Thank you very much for watching. You can leave comments for feedback.